Hi everybody, this is Dr. Schultz, and this video lesson is going to cover the physics of inclined planes, um, and it's meant to follow our activity from yesterday. Yesterday, you guys you did an experiment where you had a cart and you measured the force that acted on the cart, and then you changed the angle of the incline of the surface that the cart was sitting on. So our goal in this lesson. Our goal is going to be to find the expression for the net force, on an object that's on an incline. So I'll give you a second here to write that down. And also, you can make a sketch that shows an object on an incline. Make this sketch kind of big. I would say, really, this should probably take up like the top third of your piece of, paper in your notes. Okay, because we're going to add a lot of stuff to this picture. So do not make this small. This should be about that big in your page. Okay. All right, so we have an incline there. I'm going to add an angle theta down here. That was the angle yesterday that we measured as you lifted up the ramp. This object right here, which is on the surface, that has a certain mass. I'm not going to draw the wheels, so you could pretend that this is a cart. We're gonna assume right now that there is no friction. Okay, so we can add friction later on. So this is frictionless. Okay, so what we're going to do first is going to be to draw the free body diagram for this object. So I'm going to put a dot right in the middle. And I saw yesterday that you came up with free body diagrams for this, and I think most of you got this right. The idea is going to be that we're going to have a weight force that acts straight down. So that's mg. And we also have a normal force. Okay. Now the normal force, sometimes people think is going to be just straight up, but it's not, because a normal force is always at a right angle to a surface. So one thing that I do sometimes to cheat, or not to cheat, but to help myself to draw it, is I can take my ID, there I am, and I can actually sort of line up one edge of my ID with the surface. I can slide it along, and now when I get to that point, I can simply extend, and I've got my normal force. So if that helps you to draw a more accurate free body diagram, it's probably worth the effort of doing that right now, is to take something that has a square corner and just use it to draw the normal force. Okay. Now, how long do you make the normal force? This is a little bit tricky because we don't know exactly yet. But I'd say about that length is probably fine. Okay, so before we get into anything else with this, I want you to look at the picture. These are the only forces that act on the cart. And I hope you can tell that they do not cancel. They cannot cancel because they're not opposite to each other. And they're going to leave you with a force which actually is going to head down the ramp. I'm not going to draw it yet, but there's going to be a force which points downhill. And that's the force that we're trying to find. Okay? Sometimes that's called the parallel force. So the question is how do you get that? How do you figure out what the expression is for that force? And the thing to do is to recognize that the object, it's going to move in the direction of the incline. And so it would make sense for us to draw an axis, like an x-axis, that goes right through the object center and is parallel to that incline. Right? I mean, that kind of makes sense because then when we get a force, that force will be in the x direction, and that's the force that makes the cart accelerate in that direction. So this is kind of common sense in a way to make your axis align to the surface. Alright, so if we put an x-axis there, that means we're going to have a y-axis that's perpendicular. And, this is wonderful, the y-axis lines up with my normal force. Right? Because the y-axis is perpendicular, so this is y. So that's kind of the hard part, right? Is figuring that out. Because now if you look at this picture, you can see that the weight vector, which goes straight down, the weight vector is going to have a component which goes in the negative y direction. And the weight vector is going to have a component which goes in the positive x direction. And those components are going to be what determine the motion of this object. So how do I find the components? And the idea would be that I want to draw a box around the weight vector. Okay? And my box has to have sides that are lined up with my axes. So I'm going to take my ID again and I'm going to kind of slide it up. Okay? So that I'm lining up this edge right here. And I'm going to go to the corner here and I'm just going to extend a little box. Or a line. Okay? So now this dashed line is parallel to my y-axis. I'm going to do the exact same thing over here. I'm going to complete the box right there. So now I have this rectangle in here. And the weight vector is my diagonal. Okay. And so the reason for doing this, okay, if you recall how we found components for projectiles, is we're going to do the same thing now, except now you have a force. And that force has components. And the components are drawn from the origin to the ends of the box. So I'm going to draw that component there. That is the parallel force. Okay, because it's parallel to the incline. So that little arrow there actually represents how much force is pulling the objects down the incline. And if there is no friction, then that parallel force is going to be the net force on the object. Okay, so that's really what we're after here, is to find that. As long as we're drawing this, let's also show the other component of the weight. So there's another component that goes this way. And this component is going, basically, it's the component of the force that pulls the object down into the ramp. Alright? And it's a downwards force. And this force is important because this downwards force is actually canceled by the normal force. They have to cancel each other because the cart doesn't really accelerate in the y direction at all. So these two forces have to cancel each other. And so we'll need this force, especially when we have friction, because this force determines the normal force, and the normal force is related to friction. Okay. So we have a really good picture right now. This is showing how the weight has two components, and the parallel component is the one that we're going to want to use for our net force. So what we have left to do is to find formulas, that relate this force to the angle theta. That's our goal. Our goal was to find an expression for the net force, and it should be in terms of theta. Yesterday, you all found that the force was proportional to the sine of theta, right? That was our finding that we found experimentally yesterday, but we didn't know why that was. So we want to get that formula right now and make sure that works. So here's what we're going to do to find it. Is we're going to look at our triangles here. We've got a big triangle. I'll complete it. Right? We have a big right triangle, which is the whole incline. And the skinny angle down here is theta. If you look inside of here, though, inside of this rectangle, we also have two small right triangles. Okay? They're nested. And the skinny angles in here, that angle, and that angle, those are both theta. They're the exact same angle. So that's true because these inside triangles are both right triangles, and they're both similar to the big triangle that we drew. Right? Let me try to zoom in on this. So this triangle here, the one whose right angle is right there, so the one on the left, that triangle is the same, has the same angles as the big one. So it has a 90-degree angle, just like the big one, and it has theta, just like the big one. And I would say, like, the way that you recognize that is just by looking to see which angle is kind of the skinny one and which one is the bigger one. And so this theta goes with that one, not the other side. And this other triangle is also similar because it's just the other half. Okay. So if we know that, that's actually really important because now you have a situation where you can use trigonometry. So I'm gonna copy this down here, and I'm gonna pick the triangle that was on the right side, I guess. And the hypotenuse of that triangle is the weight. That's mg. So the question is what is this piece? Because this piece here, that's going to be your F net, right? Your F parallel, whatever you want to call it. And this piece over here, this long piece, that's going to be the part that is fighting against the normal force. Okay. So I'm going to call that F perpendicular. And you know what? I'm going to actually, instead of calling this F net, I'm going to cross that out. I'm going to call it F parallel. So we're talking about parallel to the incline or perpendicular to the incline, because that's kind of, a lot of times people talk about that in those terms. So so how do you find those two sides? I mean, you've got basically one side here. This is adjacent to the angle theta. You've got this other side over here, which is opposite to the angle theta. It's a right triangle. So here's where your trigonometry comes in. And so the idea would be that F parallel is going to be equal to mg times the sine theta. Okay, why is that? That's because of SOHCAHTOA. Okay, you have a right triangle. Sine theta is going to be the opposite over the hypotenuse. The opposite in this triangle is F parallel. The hypotenuse is mg. So if you rearrange that, that gives you the parallel force. And by the way, that was our goal. We've just kind of shown that the parallel force is given by the function mg times the sine of theta. Okay, so that's awesome. So actually now you see that in fact our results from yesterday are consistent with the, the physics that we understand. Okay, so that's good. The multiplier out here is important. It's always the weight of the object which is out in front, and you have this sine theta which comes in, and so that explains your graphs from yesterday. This other component, the perpendicular component, that's going to be cosine, and it will be mg cos theta. And I'll put a box around that too. And of course that's because cosine of theta is equal to F perp over mg. It's going to be adjacent over hypotenuse. Adjacent over hypotenuse. And so you have a cosine function that comes in there. This is important. This force is balanced by normal, right? So if you look back on the picture, this perp force, F perp, that gets balanced by the normal force up here. So this force doesn't cause acceleration, but this force does. It's important because it increases friction. Okay, because whatever this force is, the normal force has to match it, and then friction depends on the normal force. So when we do problems with friction, we're going to really need to use this. But if you don't have any friction, you don't usually care about that one. This is the one that you really want. Okay, so I guess to summarize here, we've used a free body diagram, and we've used it and tilted our coordinate system to come up with the force that acts parallel to the incline on an object. We also know the force that acts perpendicular on the incline. Okay. So that is good stuff. Let's do a quick example here of a problem. So, you know, the problem might be find the acceleration of, let's say, a 70 kilogram skateboarder on a 40-degree incline. Okay. So find the acceleration of a 70 kilogram, skateboarder on a 40-degree incline. And so the process here is very much the same as what we did before. You're going to draw an FBD, and then you're going to solve for acceleration. Okay, so we did a lot of problems like this last week. So your FBD can be really simple. You don't have to draw me a skateboarder. It can just be a mass, a block, whatever. You're going to have mg. You're going to have normal. Okay, those are the two forces that act on that block. Now, if you want, you can also show me, right, that you have a parallel force. And since there's no friction in this problem, the parallel force is going to be equal to F net. Okay. So that's your free body diagram. How do you find the acceleration? You use Newton's second law. You need to write it. F net equals mass times acceleration. I want you to write that over and over. And then for your F net, you're going to use the parallel force, mg sine theta. And that's it. There's nothing else. And that's equal to m times a. Then you can go ahead and substitute and solve. So the mass is 70 kilograms. The acceleration of gravity is 9.8. I'm not going to write the units on that. And you do the sine of 40 degrees. Okay. So you multiply those things together. You make sure your calculator is in degrees. And that's equal to the mass of 70 kgs times acceleration. And then it's just a matter of kind of plugging and chugging and solving for the acceleration here. So when you do 700 or 70 times 9.8, you get something like 450 newtons. And that's equal to 70 times a. And then you divide both sides by 70, and you get something like 6.4 meters per second squared. I'm not sure if I rounded right on that, but something like that, around 6.4. And that's the acceleration of the skateboarder as they go down the incline. There's a couple things to note here. One of them is that the acceleration down the incline, it's not as big as gravity. Okay, so it's got to be less than 9.8 meters per second squared. If you ever solve an inclined plane problem and you get an acceleration that's bigger than 9.8, you've done something wrong, because the biggest acceleration you could have would be 9.8. So this is reasonable to get this. So check that, right, when you're done. The direction of this is down the ramp. Okay, so that means, along the incline. The other thing that you might notice here is that if you went back up to where you wrote things symbolically, there is a little bit of a payoff here. If you write some things symbolically, sometimes you learn shortcuts. And did you notice that this term here and this term here show up on both sides, right? Mass. And so you can cancel that, which means that you could have answered this problem without even knowing the mass of the skateboarder. You could have just found the acceleration by taking 9.8 times the sine of 40. And that would give you the same answer, the 6.4 meters per second squared. So this is actually kind of neat from a physics point of view, because we've seen this before. We know from Galileo's law of falling bodies that a large mass and a small mass, they both accelerate at 9.8 meters per second squared. It doesn't matter the fact that the mass of this one is much bigger and the mass of that one is smaller, right? The masses sort of cancel out. If you're wondering why that is, if you're bothered by that, you know, you can kind of think of it this way. This mass right here, of course, has a very big weight, right? Because it's a big rock. And this mass right here has a relatively small weight. So the pull of gravity, the force of gravity, these black arrows, the pull is much stronger on the big object. Okay. So you might wonder, well, why don't big things accelerate at the same rate as small things? You know, why does this big rock still accelerate at 9.8 meters per second squared, the same as the small one, if it's being pulled so much harder? And I hope you're thinking about this right now, and I hope you're thinking about Newton's second law. Newton's second law says acceleration is always equal to net force over mass, right? That's the law that, you know, that things follow. And so if something has a really big force on it, if it's this gravitational force, well, the reason is that gravity itself is so strong because the object has so much mass. And that mass is going to do a lot more resisting here. Okay? So a big object has a heavy weight, but it has a lot of inertia. And so the weight and the inertia, right, the weight and the inertia actually kind of cancel each other out, and they leave you with the same acceleration. So you can have a big weight canceled by a big inertia. That's the same as a small weight being canceled by a small mass. So Newton's second law, when you talk about weight and gravity, it's really like you're dividing mg by g. Okay, that's what this acceleration is. F net is mg, and then you divide by m. And so mg over m, those m's cancel, and that acceleration is always equal to g. And that's actually a pretty cool thing. So I know this is not necessarily inclined planes, but it is inclined planes, because it's the same argument that you could make for something going down the ramp. Okay? All right, so I'm going to stop here and let you guys try some stuff out on your own, but hopefully that helps to give you an example of how to solve a problem with parallel force.